Assalamu alaikum. I'm Mr. Abbes Al Habib, Doctor, Student Specialty Materials Physics from the University of Mostaganem, Algeria. Firstly, I want to thank the scientific committee and jury members for the acceptance to my participation in your first national online conference in materials physics by presenting my oral communication entitled First Principles Study of Structural, Electronic and Magnetic Properties of RH2NiGe 4 alloy. Uzler compounds are generally alkyl metallics with the general formula XYZ or X2YZ, in which X and Y typically are transition metals, and Z is a main group element. This class of materials was discovered in 1903 by Fritz Uzler. A new favorable structure may be the tetragonal structure with the space group 139, often referred to as D022. In this work, we give an overview of the structural, electronic and magnetic properties of this exceptional class of one of the important 4-Isler alloy, which is RH2NiGe. The calculations were performed using the Y2K code using the self-consistent full potential linearized augmented plane wave method as part of the DFT. The exchange and correlation potential was used the GGA approximation. The energy of separation of the valence and core state cutoff was taken as -6.0 Rydberg. The process of self-consistent iterations is repeated until our convergence energy and charge less than or equal to the value of 0.001 and 0.001 respectively. The Brillouin zone is integrated with 3000 K points. In the present work, Moffentin spheroids were 2.25 atomic unit for RH and GE, 2.10 atomic unit for Ni. First, we have calculate and plot the total energies as a function of volume to get the more favorable energy for RH2 and EGA in both cubic phases. Space group 216 and 225 for magnetic and non-magnetic states. Figure 1 shows the optimization energy versus volume for RH2 and EGA alloy, where we found that the magnetic state in the cubic phases space group number 225 was the more favorable structure. Then we plot the total energy versus volume for cubic and tetragonal phases in magnetic state. We found that the tetragonal distorted structure, space group number 139, was the more favorable for the RH2NEGE compound at a temperature of 0 Kelvin. In this structure, it is necessary to determine the ratio C over A in order to find the ground state. The optimization of C over A ratio obtained with a fit polynomial. Figure 3 shows the existence of a tetragonal distortion for the studied compound. Using the nonlinear fitting with the empirical mean equation of state, we have determined the ground state properties. The obtained results are listed in Table 1. The Figure 4 shows the calculated band structure of spin-up electrons for RH2 and EGE in the tetragonal phase. Figure 5 shows the calculated band structure of spin-down electrons for RH2 and EGE in the tetragonal phase. The electronic band structure and density of states calculations of the RH2 and EGE compound show a metallic character. In Table 2, we give the calculated total and partial magnetic moment for RH2 and EGE compound. As a conclusion, we use in the first principles for potential linearized augmented plane wave method. Electronic structure and magnetic properties have been calculated for the RH2 and EGE compound. The cubic structure is unstable and the tetragonal structure lowers the ground state energy. The band structure and the density of state for RH2 and EGE compound in the quadratic structure for both spin up and spin down state confirm a metallic ferromagnetic behavior. Thank you for attention.